together in court, you guys.
Yeah. All right. Page 155 in your book has a table of all sorts of ionization energies, and it has periods 1 through 3. So it has the first 3 periods, which takes you not through the D's, but it takes you through element 18. Okay? As you read this, as you go across a period, like for first ionization energy, and that's what we had notes that we talked about, as you go across a period, the numbers get larger as you go across. So if you look at the first row that they give you, period 2, starting with lithium and going to neon, they get larger, right? And that's what we told you, that the period trend is to get larger going across it. It's more difficult to take out an electron. Does anybody remember why? It tends to be more difficult to take an electron out of an atom as you go across a period. Yes?
I guess this attracting it to the center.
Okay, so there's an attraction between the center and that electron, or that group of electrons that are getting bigger. Why? Trevor?
There's more shells.
That would be the case going down, but going across, we're not adding more shells. So why does it get more difficult? We know that the attraction is greater, but why is it greater? That's what I'm asking you. Why is it greater?
More electrons.
But there's also more protons. And what does that cause the shell to do? Shrink. So the shell, so those are all examples, like Cameron said, it gets more electrons. But as you go down the group, they also add more electrons. So if you stated that on a test as a reason, I couldn't give you credit for it. You'd have to say because there are additional electrons and protons, there's a stronger attraction between the nucleus and that shell, causing the atom to get smaller in size. So when you give descriptions, you want to be detailed in it, because we're also adding electrons down a group. And we know that as you go down a group, the ionization energy gets less. It becomes easier to take out an electron because that electron's farther from the nucleus because we're adding additional shells as we go down a group. Right? So on the next row across, sodium through argon, they do the same trend. It gets bigger as you go across. More difficult to take out electrons. So there's this idea called ie1, ie2, ie3. And all that is abbreviation for the energy to take out the first electron, ie2, the second electron, ie3, the third electron. Because you can take more than one electron out at a time. You can take multiple electrons out because you have charges that are +1, +2, +3. All right, and this is all this has to do with is taking electrons out of the atom. Okay, at what point does it becomes so difficult to take out an electron that it's almost impossible to take out that next electron? So at what point do you get to where energy is put in and you're taking out electrons? Does it basically get to the point where it's way too much? Way too much, and it's not going to happen. And that's what we're going to talk about a little bit. Okay? So as you go down the columns, let's just take a look at lithium, for example. So we look at lithium. Lithium is Li, and it's got 3 electrons and 3 protons. So lithium would have its inner shell, then it has a second shell. We have the 2 electrons here. We'll pair them up just like in an S2. And then it has 1 electron there, and this is lithium. So to take this electron out, that is ie what? 1. You guys see the energy to take that first electron out. Okay? So then what happens, we take that electron out, and now we have lithium. We have this shell here with its 2 electrons. Okay? So if we take one of these electrons out, that's going to be what? ie2. Can you guys see what happens to the energy that is required to take out an electron ie1? So what is ie1 for lithium? Somebody give me that number.
520.
520 kilojoules per mole. Okay. How about ie2, or the second electron from lithium? 11,000 what?
7,298.
7,298, thank you. Kilojoules per mole. Would you say that's a big jump?
Yeah.
Yeah. You know, jumps are relative, relative to one another. So that is an increase of probably 15 times the amount of energy would be required to take out that second electron. So that is where we talk about huge jumps, and that's pretty much going to be impossible to take out that second electron. Anybody know why? Yes?
Because it has a full shell, it's more stable.
Yep.
But if you take out the electron, it becomes unstable, so
Yeah.
you have to keep it.
Right. Full shells tend to be lower energy and lower potential energy, but there's also another reason we can actually see by looking at the model. Where's the electron located? Compared relative to each other. This one, distance. This one, distance.
The one on the right's closer to the...
Yeah, it's closer to the sources pulling it in, which means there's greater attraction for that electron. Does that make sense? All right. So I'm not going to do a bunch of these, but I'm going to do 2 of them. So the next one we have, let's just skip beryllium and go to boron. All right? So we're going to skip beryllium and go to boron. So here's the boron. It's got its 2 electrons in the inner shell. And then it has how many electrons in the second shell? 3, right?
3.
Okay.
Sure.
All right, so S2, this is 1s2, 2s2, 2p1. All right? So we're going to take out the first 2 electrons. So this electron's ie1. We'll take this electron out. We'll say that's ie2. So then we get to, and then what happens is the protons are still there, and we're subtracting out electrons. So what do you think happens to attraction between these 2 electrons and the protons in the nucleus?
Positive.
What?
Yep, the protons are positive, but what happens to the attraction between the electrons? We've got, I'm sorry, this would be ie3. Take that one out. So we take out the first 3 electrons. We got 3 fewer electrons. We got more protons. It's going to be really close to the nucleus. So to take out this electron is ie4. I want you to look at the difference between ie3 and ie4. So we're on the chart on page 155, and we're looking at boron. It goes from 800 to 2400 to 3600. And then it goes to 25,000. That's a significant jump compared to those other increases. Those other increases are kind of like it triples. And then the next one, it doesn't quite double. And then we've got an increase that is a huge amount of increase. Why? Because we're taking out, again, they call this a noble gas configuration. So anytime you're going to take an electron out of a noble gas configuration, it's going to be impossible to do. So what's the charge of boron do you think it's going to be as a cation? Do you think these 3 electrons are relatively easy to take out? The 4th is more difficult, so it's going to be a +3. All right, so let's answer the questions here really quick on this. Which group has the largest jump in ionization energy between the first and second? Where we've got big jumps occurring. So if you look on table 3, where do we have those big jumps occurring? Between which group has the big jumps between the first and second?
2, group 1.
Group 1, right? Group 1, they even highlight it for you. Group 1 has lithium goes from 520 to 7298, and then sodium goes from 496 to 4,562. Where you have a huge difference in the ionization energy is where it's going to stop taking out electrons. At that point, And we know what that point is when that outer shell is gone. When the outer shell is gone and we go to the inner shell, that's when it's not going to take any more electrons out. And that's what will give you your charges. Okay? Why such a large jump in ionization energy? We can say that now electrons are taken out of an inner shell. So if you want to write down, the reason for a bigger jump is because electrons are taken out of a noble gas configuration, or electrons are taken out of an inner shell where electrons are closer to the nucleus. Okay, put it in your own words. Okay? So what's the reason? Why does that happen? Because electrons are trying to be taken out of an energy level that's closer to the nucleus than the outer shell would be. Which area in the periodic table shows a... no, I'm on the wrong question. Group that has the largest jump in ionization energy between the second and third. So look at your columns and look at the highlight, how they have it highlighted. Where do we get big jumps between the second and third? Which group? Group 2. Group 2. It would be beryllium and magnesium. If you look at those two, you got huge jumps between the second and third. So on a test or on a quiz that you'll have on Thursday, I will ask you which group has a large jump between the first and the second. You say group 1 because you would know that once you get rid of that outer shell electron or outer shell electrons, then it becomes pretty much impossible to take electrons out of an inner shell. Okay? And I could do any of them. I could do groups 1, 2, or 3. Any of those groups. Okay? Any questions on that? All right. So it asks why such a big jump. You can use the same reason as you did for the first one. Okay? Because you're taking electrons out of an inner shell. Yes, ma'am.
Are we going to have graphs on the tables on the test?
No. What you'll do is you'll get to practice today. What you get to do is you get to use your periodic table and use the trends to practice the concepts that we have been talking about, the trends. But you won't be able to look at the... What I'll do is, like I told you, you're going to predict the trend. You're going to predict which one's bigger or smaller. So, Shane, for example, I'll ask you, which atom's bigger, calcium or potassium? And you'll go, well, the period trend is to get get smaller going across. And so the one that's larger is potassium. Because I know the trend is to get smaller going across. And then what you'll do is you'll look on page of atomic radii on page 151, and you'll confirm if that's the right answer or not. So when you look at that, is potassium's 227 and calcium's 197. I am right because I know the trend. I know what happens as the size of the atom goes across and goes down. So you get to use those ideas and trends. All right, group with a lower first ionization energy. What's the group with elements that would be lower ionization energies? Group 1. Yeah, group 1. Okay, are you filling this out, Dalton?
A little bit.
Yeah, why don't you focus on this here and fill that in as we go through it, because I know you might have questions on that later on, okay? Okay, thank you. What does the group, or why does the group have a lower first ionization energy? And the reason because the atoms are larger. That's the reason. It's easier to take out electrons, and they're larger atoms. Meaning that the electron's farthest away from the nucleus. Okay? All right, so what you've been waiting for, and I'm going to hand you out, is the worksheet. And in period 1, got this worksheet before we went down for the assembly. So you will work through this and use your book to reconfirm the answers to see if you're getting them right. They have the answers. You will know the answers because you can look them up on those periodic tables that have the numbers.
Say that. Going back home.